Hello, my name is Christopher Jelesnianski, and today I'll introduce our work, MARDU, an efficient and scalable code re-randomization defense technique that deals with preventing return-oriented programming attacks. So what is return-oriented programming? Return-oriented programming, also known as ROP attacks, are a security attack that was introduced to bypass data execution prevention. ROP attacks reuse portions of a program's code, known as gadgets, against itself to construct an attack and achieve arbitrary code computation. Address space layout randomization, also known as ASLR, was introduced and widely adopted to combat early return-oriented programming. However, soon after, variants of ROP, such as just-in-time return-oriented programming and blind ROP, were developed to overcome current defenses. This brings us to today, where execute-only memory and code randomization defenses are an effective means to dealing with ROP attacks and its popular variants. ASLR was an early ROP defense that is very lightweight. However, a single code leak can compromise and expose the entire code layout to an attacker. Re-randomization sought to fix this loophole with the intuition that continuous churn of code would make constructing ROP attacks much more challenging. While re-randomization is much stronger, it often comes with a trade-off of having high overheads. So overall, it can be said that current defenses are effective but not really practical. In general, for a defense technique to be as easily adopted as ASLR, it must have three key properties. It needs to be performant, it needs to be a strong defense, and it needs to be scalable such that the defense can be applied system-wide. In practice, most techniques can achieve two out of these three desired properties, but achieving all three is challenging, especially for re-randomization. A recent randomization technique such as Code Armor has a great average performance overhead of only 3.2% and protects against popular ROP attacks. However, it does not support code sharing and requires a per-process background thread. So now that we've set the stage for return-oriented programming attacks, we can further discuss the challenges related to re-randomization techniques. Our work, MARDU, sets to address all three key challenges. We'll briefly describe how MARDU achieves each, and we'll go into more detail next. So for security, a single code leak can disclose the entire code layout. MARDU utilizes execute-only memory to protect all sensitive code regions an attacker needs to create a ROP attack. For performance, most randomization techniques are active and continuously randomize code, regardless if there is an attack happening or not. This takes up valuable system resources to provide a defense. Instead, MARDU performs randomization reactively, only when needed. Finally, for scalability, most randomization techniques require costly code tracking and patching mechanisms to maintain program semantics. Current randomization techniques are also not capable of sharing randomized code. MARDU utilizes code trampolines to both minimize patching overheads as well as have a way to securely share code. So we'll now present the design of MARDU, and first we'll go over what code trampolines are and how MARDU leverages them to achieve security. In a traditional control flow, when a function is called, like foo or bar, a return address is saved and the control flow jumps directly to the function body. At the end of a function, we use the saved return address to get back to the previous call site. This traditional control flow exposes the return addresses on the stack to being corrupted by vulnerabilities such as buffer overflows. Trampolines are a coding paradigm that provide a level of indirection. With this, trampolines can hide the actual location of function bodies, making gadgets much more difficult to obtain. In addition, by being immutable, less code tracking and patching has to occur overall during runtime, minimizing performance overhead. MARDU therefore protects forward edges, like function calls, by instrumenting code such that all forward edges use a trampoline region for control flow transfers. MARDU protects backward edges, like function returns, by leveraging a shadow stack. Traditionally, programs use a single stack to store data for the current function as well as the return address. MARDU separates the usual stack information and specializes a shadow stack to specifically store, hide, and protect return addresses from vulnerabilities such as buffer overflows. Finally, MARDU introduces entropy throughout runtime by randomizing code layout at both program startup as well as on demand whenever an attack is detected, such as when a process unexpectedly crashes. So now to demonstrate how MARDU uses trampoline, taking the same program as before, the MARDU compiler will have instrumented all code into a code region and generates a trampoline for each function body and function return for each call site. The MARDU runtime will also set up a shadow stack to protect the return addresses. Assuming again someone has called foo, when we reach the call site for bar, we first populate the shadow stack with the appropriate return trampoline address and then jump to the corresponding trampoline for bar. The trampoline then forwards us to the randomized location of bar, and we execute the bar function. Once it's time to return to the previous frame, foo, we fetch and pop the top element of the shadow stack and go to the corresponding return trampoline. which finally returns us to foo, allowing execution to continue. It should be noted that both code and trampoline regions are protected by execute-only memory via Intel memory protection keys, also known as MPK. By covering these sensitive regions with MPK, any attempt to read or write these regions will cause a memory permissions violations and crash the application. This will then trigger re-randomization of any associated shared code still being used by other processes. So next, we show how MARDU enables scalability by achieving sharing of code among multiple processes. MARDU is the first randomization scheme capable of runtime re-randomization and code sharing. Trampolines are a key design aspect that enables MARDU to have this code sharing. So to explain how MARDU loads and shares code during runtime, let's assume we have a MARDU compiled binary that has the instrumented code and newly generated trampoline code. In addition, the compiler creates a new section that contains offset information for updating and patching code to remain semantically correct throughout re-randomization. This includes things like control transfers and memory references. When MARDU runtime starts, it first maps a code cache in kernel space. Then the trampoline region is mapped to the end of the region. Next, the code region is randomized at function granularity and also mapped in. Finally, all necessary fix-ups are patched to maintain semantics. After this, the program proceeds and executes as normal. Note that this process is the same for both programs and shared library code. So now, assuming we have a MARDU-enabled libc, if we have a new MARDU-enabled program start up like a web server, it'll first perform its own MARDU randomization and then simply map a virtual copy of the MARDU randomized libc into its user space memory and use it like normal. The same process occurs for any other MARDU-enabled program. So finally, we show how our MARDU design performs re-randomization during runtime without needing any stop-the-world mechanisms. With the same two MARDU-enabled programs as before, currently running and sharing a MARDU-enabled libc, in the case that the database server is attacked, this usually means that the database server and all associated library code is now exposed to the attacker, meaning without any defenses, an attacker could now leverage this information and make an attack on the web server process. However, with MARDU, the attack on the database server will trigger re-randomization. Let's see. When the attack is detected, let's assume the web server and database server using version 1 of libc denoted as v1. When re-randomization begins, we set up a new mapped area for libc to be re-randomized denoted as v2. We re-randomize and patch as done before. What happens next is to specifically handle not stopping the world for a MARDU process. For a brief time, we actually allow both code versions to exist in user space, such that the web server process does not need to stop in case it was executing libc code when re-randomization was triggered. This is possible because MARDU trampolines are immutable, allowing the return address of the trampoline to always be correct. Once the reference count for the first version reaches 0, we can safely unmap the old version of libc and unmap the kernel memory for it as well. This process makes any gathered information, if any, stale and useless to the attacker. And then to further clarify, this re-randomization scheme is repeated on demand whenever an attack event is detected for any number of associated code that might have been compromised. With all these techniques, we're able to make MARDU performant. In essence, MARDU wants to always be one step ahead of the attacker, which can be seen similar to how the con artist is always one step ahead of the FBI agent chasing him in Catch Me If You Can. So we have created a working prototype of MARDU, which consists of a compiler and runtime components, where we used LLVM for implementing the MARDU compiler and made a few Linux kernel modifications to support our runtime. In addition, we used Muscle, a simplified libc implementation. Next, we'll move on to the evaluation. So for our prototype, we're able to evaluate MARDU on the three important fronts that we've been talking about throughout this presentation of security, performance, and scalability. For security, one popular attack variant is code inference attack. These attacks set out to use a code vulnerability to leak a code addressed to the attacker, and with this, leapfrog across functions to eventually uncover the entire code layout. MARDU circumvents this by protecting the entire code region, including trampolines with execute-only memory. We evaluate MARDU against a few other attacks, however, please see the paper for this analysis. Finally, we look at MARDU's performance and scalability. For our performance evaluation of MARDU, we use Spec CPU 2006 as a compute-bound benchmark suite. We evaluated all C language benchmarks as our current prototype does not support C++. However, MARDU could support C++ with additional engineering effort. In addition, we evaluated MARDU with the Nginx web server as a concurrent application for evaluating scalability. For spec, we achieved an average runtime overhead of 5.5%, and in the best case, MARDU had a negligible overhead. We also evaluated MARDU in a concurrent setting using Nginx and measured throughput. Across various worker counts, we only observed a 4.4% average degradation in throughput. For scalability, MARDU's re-randomization latency scales approximately linearly with the number of fix-ups required. For spec, the average number of runtime re-randomization latency was approximately 6.2 milliseconds. In addition, it's important that a defense is scalable even when under heavy attack. Therefore, to stress test MARDU, we also evaluated it under a simulated attack scenario, varying how often re-randomization was triggered. As we can see in the figure that even for GAB-MK, a benchmark with a larger number of fix-ups, the re-randomization latency stayed close to 15 milliseconds for all intervals. For more scalability evaluation, please refer to the paper. So in summary, we proposed MARDU, a randomization defense aimed at addressing return-oriented programming attacks and its popular variants. MARDU is capable of defending against all known ROP attacks while also achieving good performance and scalability. MARDU does this by being an on-demand reactive randomization approach compared to past works that were active or static. Finally, MARDU is the first randomization scheme capable of supporting runtime re-randomization and shared code, giving MARDU the scalability to protect code across multiple processes. Thank you for listening and your interest in MARDU.